Okay. Today we have our own Mike Stillman from Cornell University, who's going to tell us about Batyrev's construction for Calabi-Yau threefolds.
Hey, thanks. Thanks for coming. I'll try to see how much I can get. No, I'll do this normally. Oops. So today what I want to do is I want to define what a Calabi-Yau is, go through some little features of it just to get comfortable with the basics, and then do the Batyrev construction, which I don't know. I just always thought it was kind of like, oh yeah, did this. But then once I got to get to know it better, I appreciated the subtleties in it more. But at any rate, so we're going to do Calabi-Yau threefolds mostly, although actually we'll start off with anything, and Batyrev construction. Batyrev construction. I am not assuming that you are comfortable with torque varieties or fans or anything like that. So we will. So that's where we're starting at as far as this goes. Okay. So let's just start first of all, though, with the definition. As soon as I say it, and now I'm not going to assume something. Here's the definition. Okay. So let's let X be a smooth projective variety. There are also, well, here I'll say it first. X is called Calabi-Yau, which I will almost always abbreviate to CY. It's called Calabi-Yau if the following two conditions hold. If A, the first one is just some things in cohomology on X. So O of X, H2 of O of X, all the way up to H to the dimension of X, not the top one though, -1 of O of X, these are 0. Even if you don't know any algebraic geometry, you have to appreciate that all these zeros on homology or cohomology makes your life infinitely easier than if it were not. Okay, so in fact, it's totally unreasonable how physicists are completely lucky in that regard. But anyway, okay, so we have that. And then the main, well, that's an important condition, but the other condition is that if I take the canonical class, well, I take a top differential form, rational. I just take one, and I start on all the open, I just figure out what its zeros and poles are. And I find that I can actually find one of those things that has no zeros or poles. So it's linearly equivalent to 0. So this is the sort of flatness of this. And Calabi had a conjecture that if you had something that implied this, then it had a really nice metric, a Ricci flat metric and things like that. And Yau actually proved this result. And so that was one of his first big theorems. And but anyway, I don't expect you to feel like that this speaks to you. Okay, but nonetheless, this is the definition. Mathematicians will oftentimes also try to extend it to singular stuff, but that sort of gets technical, and from the physics point of view, they don't really care about it because they really need the thing to be smooth. So I'm not worried about that. Yep.
You could think X equivalent to 0 thing is like there's some patch where it's Gorenstein.
Yeah, this is a very much of a Gorenstein kind of thing. In fact, we're going to see Gorenstein thing. We're going to see reflexive polytopes. All these things are incantations of Gorensteinness, but we're not going to talk about that too much today. But yeah, that's what that is. Okay, so let's do a few first examples. Okay, what are the examples of these things? It's really nice to have. Oh yeah, we have these blah blah blah. You know, but we need some examples. So soon, once we do the toric stuff, we'll have lots of examples, but nonetheless, they all just generalize these things. So let's let X be contained in Pn. I'm going to take n to be 1, 2, and 3. Sorry, 2, 3, and 4. You know, some small values at the moment. but it doesn't matter, it could be anything. Let this be a hypersurface of degree D. And let's suppose that's at least, I don't know what it has to be, at least maybe 1 or 2, right? You know, whatever. So it has to be some hypersurface. And we're interested in when is X Calabi-Yau. The great thing about hypersurfaces in projective space, once you first learn the basics on cohomology, is that you note that, so this has dimension n-1 for starters, because of the hypersurface, and you get that h1 of O of x all the way up to hn minus 2 of O of x, which is the same range we have up there. This is 0, comes for free. In other words, any it doesn't have to be Calabi-Yau, but any hypersurface will have this property. Yep.
That just means like paper surfaces.
Kind of, yeah. I don't know if that actually is just around the same notions or if that actually proves it, but it's yeah. So this is everything's projective. So this comes about from the short exact sequence of this as a there's a short exact sequence, and then once you look at it, you get all of these have to be 0. Okay, that's one of them. What about the k of x? Well, it turns out that by adjunction, there's a formula that that's actually a really important one about how to compute the canonical class, the k of x on here, given the one here. And in fact, what it is k of x is equal or linearly equivalent, same thing here, to not the same thing, but I'm treating them sort of similar. So k of x is equivalent to, I take the canonical class on Pn, I add the class of x to it, and then I restrict to x. Again, that might not speak to you much, but you can say what this is. This k of Pn, here, let's just do it over here. So k of Pn is equal to minus n plus 1 times a hyperplane section. H is equal to a hyperplane in Pn. Let's do hat here, a hyperplane in Pn. Okay, because I want to intersect it with x, and I'm going to call that h. Okay, and now in x itself, if it's degree d, is d times h. So this is, so k of x will equal minus n plus 1 h hat, oops, plus d times h hat, and then this whole thing intersected with x basically, which is minus n minus 1 plus d times h, where h is the hyperplane section on x. Okay, so this thing is linearly equivalent to this. When is this equal to 0? It's equal to 0 only when this thing is 0. So x is cy3 if and only if this is 0, that's d is equal to n plus 1. Okay, so this is just the, once you do a little bit of algebraic geometry, this kind of computation you've done on a number of situations, and this is one of them. But it doesn't really matter. I want to now just say what it means for small d, what small n. So what is it? So if n is equal to 2, n equals 1, we're a hypersurface, it's just going to be a bunch of points. That doesn't really count. So n equals 2, though, we have x is contained in P2, and it's degree 3. So this is degree 3. This is an elliptic curve. So the point is that cy3 of dimension 1 is equal to is the same thing as a, I'm using elliptic curve just meaning the genus is 1. I don't necessarily have points on it. Yeah? 3-dimensional. Did I say cy? Oh, no, that's not what I meant. Sorry. I'm so used to using cy3 meaning 3-dimensional. I never do any of the other dimensions that it just sort of goes with the hand. So this, but this is a Calabi-Yau of dimension 1, and that's an elliptic curve. Okay, so that's in fact what this is generalizing, or our genus 1 curves, elliptic curves, that kind of stuff. Okay, how about n equals 3? Now we have a surface inside of P3, and it's of degree 4. This is a quartic surface. Once you take some algebraic geometry and you take a class on surfaces, you can figure out where this fits in the whole classification thing. This is what's called a K3 surface. Okay, and then n equals 4. We have x is contained in P4, and it's degree 5. This is a dimension 3 quintic surface.
Sorry. Over there, I think there are two different n's that should be different. They're Pn and also Hn minus 2.
Those are the same.
The same?
This n is this. This is equal to dimension of x minus 1, because dimension of x is n minus 1.
Oh, you're assuming dimension of x is n minus 1.
It's a hypersurface.
Oh, right.
So
Of course.
so
I missed
every
that.
hypersurface will be a
Okay.
dimension 1 less. I mean, there's other things we could do. We could take a complete intersection and try to figure out when it is. The same kind of game works there if we wanted to do that, and we get a handful of cases.
But a CY3 doesn't have to be all hypersurface, right?
No, not at
Okay,
all.
okay.
But this is the first case. This is the case that string theorists got very interested in the 1980s, and this is by far the most worked out example of a Calabi-Yau. But there's a lot more, and they have a lot of each one has just its own intricate behavior, and it's kind of very cool. But this is what we're generalizing here. So whenever you think Calabi-Yau threefold, you can think, oh, it's quintic hypersurface. This thing has some number of lines on it. I forget exactly, 2875 or something like that. But it's actually, it's kind of boring as far as Calabi-Yau threefolds go, to tell you the truth, because it's just hypersurface. Anyway, so this is the main example. Well, how can we modify this construction? One way to modify it is to consider a complete intersection inside of here. Another way to modify it is to take a hypersurface and a product of projective spaces. So how about if I take X contained in Pn n1 cross ... cross P of nr, a hypersurface in here. Okay. Again, you can work through the adjunction formula works very similarly, and all these H's are relatively okay too. So I'm not going to go through this. I'm just going to state what some of the other ones are. So for instance, the ones that are CY3s, so i.e. dimension 3 CY of this form, and these are all of them actually. So there's this one here, and then there's X is contained in P3 cross P1 of degree. So now to give something in here, you have to give a by degree, right? So I give a degree here and a degree here, and if I take degree 4.2, degree is equal to 4.2, that will give me a Calabi-Yau. Basically, what I have to do is whenever I have a product of these things, the number there has to be just one more than this, which is what's happening here. The degree is one more than this. Okay, so that's one of them. Here's another one. There's in P2 cross P2, basically I have to have the numbers add up to 4 in order to get a threefold somehow. So here I get X is contained in here, and its degree is 3,3. Sort of a bicubic equation. What are some other ones here? X is contained in P2 cross P1 cross P1. And this is of degree, now it's a triple degree, it's degree 3, 2, and 2. So we have 3 variables here, 2 and 2, and so that's in 4 plus 3, 7 variables. We have a whole ton of monomials like this, and we take a hypersurface in there. As long as it's smooth, then it will be one of these things. If I don't have to make it smooth, right? One hypersurface in here, I could take a monomial. That would not be very interesting. So it has to be kind of general in order to do that. And then finally, in this land, we get P1 cross P1 cross P1 cross P1, 4 P1s, and the degree is 2, 2, 2, 2. That's called the tetraquadric or tetraquartic, tetra something or other. So we have this kind of thing. These are all reasonable examples of Calabi-Yaus. If we wanted to go to complete intersections, which we're not going to do, but complete intersections, Calabi-Yau threefolds, which are complete intersections, in products of projective spaces. Now they add up to more than 4, probably. The number of those different sets of numbers that you can get that way. Actually, there's an infinite number, but if you look at some sort of equivalence of it, as it turns out, you get 7,890 different cases. They're not all different, but they're at least presented differently. Okay. So this is pretty cool. This is a huge number, and a lot of people in physics spend a lot of their time looking at these particular ones. And in physics, it's kind of like in theoretical physics, it's like the laboratory. You can't go do experiments, but your laboratory is all of these Calabi-Yaus that you have handy, and you're trying to find ones with properties that match what the universe might have. Yep.
So does this mean that we cannot keep tapping on more factors and
you could keep adding in like another. So if I had a P1 and then I take a linear thing, that's going to give me the same. So we have to avoid things like that.
as long as we have one that it's fine.
Yeah, it's a little trickier than that. It turns out it looks like there's an infinite number of these things. But you can easily show that certain ones are equivalent to other ones. So it's a little bit more involved, but it's not that bad. And this is a reasonable one. The trouble is that these are all toric varieties, right? And these are all toric varieties, and this is what we're going to generalize up here. Now, this would work as well, but we're going to do that one. By the way, so do you know why Calabi-Yaus actually have their name? I feel like I have to say it because when you hear it in physics, it's just kind of, I don't know, it always gets lost in the physics somehow. And
Calabi had a conjecture that Yau proved, other than that?
yeah, so yeah, Calabi, that's why they're called Calabi-Yaus, but why are they interesting to physicists? So I'm just going to say this instead of write it down, if that's okay. So if you're looking at certain kind of field theories in physics, and you want it to have you want it to include gravity and electromagnetism, all these different things, you're led for various reasons to a 10-dimensional total space. But we only see 4 dimensions, so there's an extra 6 dimensions floating around in there. Okay, fine, there's a 10-dimensional thing. But then there are the Einstein equations of motion that if you solve it, you get the vacuum for your theory. And this is it. You take the Einstein equations of theory, which were done in 4 dimensions by Einstein, and you just take the same equations essentially and say what they are in this 10-dimensional thing. The condition for it is you get a whole bunch of really nasty looking PDEs. At that point, I, as an algebraist, would go home. But what they did is they say, well, wait a second, the solution to these PDEs is a metric on a manifold. And that metric is the metric of this, if it's a flat metric, if this K of X is equivalent to 0. So what's really cool about this is they were interested in PDEs and solutions of it. But what they do is they translate it into this geometric thing where this geometric object has its metric a solution to those things. So they've switched a PDE thing into a geometric question. Okay, you might say, well, that's fine, but then how does the geometry have anything to do with it? Turns out it has a lot to do with it. All the fields in the theory come about from things that are happening on this extra 6 dimensions that you have. And and how much that is, well, for instance, these different copies of PNs are giving you different fields on your space and things like that. So there's all sorts of stuff, but I find it really fascinating that they're interested in PDEs and they can switch it to a geometry question, which all of a sudden then involves us as algebraists.
And so it's 6 real dimensions and therefore 3 complex.
Exactly, 6 real, and actually that's a good point. It doesn't have to be complex. It could be just real, although I think that there are some results that say it really should be complex. But as far as they can, I think the only reason they're really interested in this kind of case is this is the only case they can possibly compute with. And and there's enough of these that to keep them going for a while. So so that's sort of what I think is going on with that. Okay, so anyway, this is just somehow what Calabi-Yaus look like. They're very nice varieties. You can actually imagine working with them. They're not quite as nice as rational varieties. Rational varieties, you have much simpler behavior. This afternoon, I'll talk about if I have a Calabi-Yau, like a given along these lines. So what are some of the things we can actually compute with them, and which we can do in Macaulay too. But for now, I just want to go through the construction that is a really pretty good construction. I want to do Batrev's construction. (1993). Now I got to say, when I first read this paper, after I started talking to physicists and things like that, I didn't understand it at all. You know, it uses lots of first of all, some of the formulas have typos in them, and you want to really use a typo. So, I mean, you're a little afraid of how that goes and so on. But those are minor things in the end. So, but it was not so minor when I was first starting out. Okay, so this construction is, instead of giving this, the number of Calabi-Yaus that we're going to get from this construction in 3 dimensions, right off the bat is going to be more than 500 million. Okay, and in fact, it could be more like 10 to the 120 because you also have to triangulate some polytopes and things. But it's a finite number, and there's a conjecture that there are only finitely many Well, you know, you can find an infinite number of them. If I just take different coefficients to my hypersurface, I get a different one, right? So that's an infinite number, but that doesn't count. There are only finitely many algebraic families. Of Calabi-Yau threefolds. Okay, but the number is actually quite staggeringly high. But still, in physics, it's kind of very different from the usual. A lot of physicists even have that wrong a bit. They think that what you're doing is you have so many parameters that you can just tweak that, you know, what's the point of the whole game? But really what it is you have a finite number. It's a huge number. Maybe you can tweak it. But once you choose it, it's discrete data. And then the whole machine runs, and you don't get any more choices after a finite amount of data that's discrete. So you're not allowed to just tweak the mass of something. You know, it will be given to you. And how you compute that? That's an awesome question. We're not going there because it's not really well understood still. This was proved, by the way, if you have Calabi-Yau threefolds that are fibered over, that are elliptically fibered, basically. Have an elliptic fibration to a surface. But Mark Gross proved that in the 1990s, but it's way open still here. And to tell you the truth, I keep finding there are more and more constructions of Calabi-Yaus. I frankly am not 100% sure I completely believe that it's a finite in number. It's just so huge. But on the other hand, people who really work hard on these things, they just really believe that it's finite. So. Okay, so anyway, what are the ingredients Might have to switch me over to the next one. Is anyone on the line? It looks like there are.
Rest of clones.
Oh, sorry. Yeah, which one is it?
Ah. Okay, so the ingredients of the construction are going to be the following. This is our checklist. Going to be reflexive polytopes. And they're dual. There's two, they come in pairs. And then this is going to be a fan, let's say sigma 0 of this. Like the normal fan or something like that. That's not a very good one. Instead, what we have to do instead is we need to triangulate. Let's call this delta, and I'll talk more about that. Triangulations. And then from this and from, so if we have a triangulation, that's going to be we're going to get a simplicial fan, basically. Don't worry, this is not the whole thing. I'm just trying to put out ahead what all things are so we know where things stand when we go through it. Then we're going to have the sigma. I'm going to call this sigma the triangulation with simplicial fan. This thing gives rise to a toric variety, a simplicial toric variety. This P of sigma is precisely the product of projective spaces in those cases there. And then we have, in projective space, we have the idea of coordinate, we have the idea of degrees of elements, like in a polynomial ring. And so we have that here too. We have the homogeneous coordinate ring. The Cox ring of P of this, which is multigraded. Let's call that S. And then what we do is we take a random sum of monomials of S. It doesn't have to be that random, of a given degree. And that given degree is not is completely determined by the other stuff. For instance, degree 4,2 or 3,3 in those cases, and we get an F, and then X is equal to the zeros of F contained inside of this P of sigma. Okay. Now this is true in any dimension, and this is what we're going to talk about. This is the construction here, essentially. Okay. So what I want to do is I want to go through it on an example, a very simple example, which is the following one. It's a 2D example. So this is going to give us a two-dimensional one of these things. So a hypersurface, and there'll be one-dimensional. So it's going to be an elliptic curve. Okay, so that's what we're going to be doing here. And so dimension of, and then after that, we'll see what needs to change when we go up to 3D and then 4D. And because really we need it in 4D. Okay, so we're going to consider the following polytopes. So there's two, whenever you do toric stuff, there's two sides of the game. There's M, which is Z2. And then over here, there's N, which is the dual lattice, Z2, in a dual vector space. So here, MR is R2. And NR is R2, which is just MR dual. You know, the dual vector space. Okay, so we have pictures on both sides. I like the way I think of these things is I have a picture and another picture. They're both going to be pictures of the same thing, but one of them is sort of giving it to you via equations, like codimension stuff, and the other one is giving it to you by geometry. It's the explicit versus implicit way of thinking about these things. So over on this side, we're going to give a polytope, and we're going to give a polytope over here. So here, the polytope I'm just going to choose is a very simple one. It's going to be a square. Okay, so delta is this polytope. Okay. Then I'm going to define one over here, which we'll define in a second. This is going to be the dual polytope. In this example, this is going to be this polytope. So this is going to be delta circ 0. I don't use stars because star gets way overused in this game. Okay, so so we're going to have this pair of things. Okay, and these polytopes, polytopes form a these polytopes form what's called a reflexive pair. Okay, what is a reflexive pair? So let's just so for us here, let's start over here again. So for us, all polytopes will be lattice polytopes. In other words, they're vertices. They're convex for starters. Okay, I only deal with convex things, and all their vertices are given by integer points, integral value points, and both of these are like that. Lattice polytopes of full dimension. It's kind of annoying to deal with the lower dimensional. One can do it, but then one has lots of other annoyances to sort of keep working out. But anyway, so these are going to be, so our delta and delta circ are like that. And then in this case, they're the polar dual. So I should say if 0, which is the origin, is in the interior of delta, we have the polar dual is the following. So it's going to be the set of delta circ is going to be the set of elements y in the other lattice NR. So, well, not the lattice, just the y in here, such that if I take the dot product of y and x, I get at least -1 for all x in delta. Okay, so this is, I don't know, have you all pretty much seen the polar dual? No? Okay, so we'll talk about this in a bit. Yeah, so what is it over here? The key point of the polar dual is that if I take like a maximal face here, like this edge here, what is it? That's given by some equation, right? And that equation is going to basically be the equation 1, 0, or maybe the negative of that. I'm not going to worry about that, but I think it's 1, 0. Sorry, 0, 1, right? So this direction is the vector 0, 1, and that is the point 0, 1. That's this point. So we have a point here going to the face over here. Okay. So in other words, the points over here are giving you the equations of the bounding hyperplanes here, or at least it's not telling you where it is, but it's giving you that information. And so vertices here, and this is a dual situation. If you think about it without, because it's the hyperplanes bounding anyway. So note then that if delta circ is this guy here, and I do it again, I get delta back again. Okay, if 0 is in the origin.
Find up to dilate. Is that right?
I am defining them exactly at the moment.
Why do I not get something smaller when I try to go back? When I take this edge.
I'm taking the smallest integer ray in there. So this edge is going to be is pointing to 1, 1, right? And so that's what I'm using over here. And that edge will give me this point right here. So yeah, in this lattice game, we're always taking somehow the first lattice point along any direction. So this is what's called a reflexive. So I didn't actually say what reflexive is yet. So let me do that. So delta is called reflexive. If delta circ is a lattice polytope. Okay. And once that's the case, delta circ is also reflexive, and therefore delta circ is also reflexive because its dual is a lattice polytope. This thing is also reflexive. So this is what's called a reflexive pair. It turns out that every reflexive polytope has precisely one lattice point in the interior, like this and this, and that they combine. So in dimension 2, one might ask how many reflexive polytopes there are. Christian was talking about this in his talk, but there are 16 different reflexive polytopes in that case. And if you want to see what they all are, look up, go into Cox, Little, and Schenck in the toric varieties book. They have one page with the picture of them all. Which I like because when Hal was a grad student, we were using we always had to go find this page somewhere else, and that's I think why he put it into the book so he would have it handy. So in any case, so this is the game. We start with a reflexive pair. Okay, so where were we in our game? The reflexive polytopes. Really, what it is, it's delta and delta circ is a reflexive pair. And the way you should think about it is that there's a duality. So vertices here correspond to maximal faces here. If it were higher dimensions, lower dimensional faces would correspond to the complementary dimension face here and so on. And then that actually appears in the 4-dimensional case. 2D examples are great, but they have one really big problem with it. And what is the problem? Is it conflates codimension 1 and dimension 1. This is actually a serious problem. This is why when people in algebraic geometry were doing surfaces, the theory was all done, not even really trying to figure that out. And it wasn't until essentially the 70s and 80s that Mori and others were able to break apart and really sort of separate the concept of codimension 1 and dimension 1 to get the higher dimensional higher dimensional algebraic geometry to actually take hold. You had to think about things just differently. And it's no harder, but we all had to relearn things to do that. So kind of interesting. Nowadays, I don't think people have to relearn it because they're taught that from the beginning. So I have it harder that way. Okay.
Remind me, why did you put a knot on the fan on the second line?
Yeah, I'll get I haven't got there yet. So yeah, in fact, we won't really see it at the moment. When we get to higher dimension, that'll appear. But so first of all, so this is reflexive. The number of these things, number in dimension 2, there are 16 of them. Number of these in dimension 3, I think there's 4,319. And then number in dimension 4 is 473,800,766. And each one of these will give us actually a number of these Calabi-Yaus. Okay.
This one in particular is P1 cross P1, correct?
This is yes, this is P1 cross P1. In fact, I did that on purpose. I was going to put this on the other side. But anyway, yeah, this is P1 cross P1.
And then you take a random sum of monomials of the given degree.
Degree 2, 2.
2, 2 specific.
In that case. And that's not that many monomials in there. So, but it will turn out that's going to be an elliptic curve, and that's going to be this thing here. But we'll get to that in a bit. When I say there are this many, there are actually a lot more. I mean, but but up to equivalence under an invertible integral linear change of basis. And that's all we care about. So that gives us this. Okay, so step one is now done. Reflexive polytopes. Okay, step two is we want to make a fan out of this. There are two ways of doing that. Once you start doing torque geometry. So what is a fan? Just a bunch of cones that when you intersect any two cones, you're still in the set. So the fan here, we're not going to ever take a fan over here. We're going to take, it's a little easier because of the reflexiveness than it was in the case of, actually I forgot, this goes until 1120, right? Okay, let me, so here is the fan that we have here. We take the origin and we just take all of the vertices and then make the fan. Actually, in higher dimensions, we'll take the fan over every face, basically. Okay, so this is going to be sigma. Here is this fan. So we have a cone here, a cone here, a cone here, and a cone here. How are people with cones and faces? Does this make, is this okay or not okay? Do you want a little bit more information? Yes, it's okay if you do. So so the way I think about it is this is a fan is just a bunch of cones. So we have 4 cones here. Say sigma 1, sigma 2, sigma 3, sigma 4. And we also have rays. Let's call that row 1, row 2, row 3, and row 4. Okay, and the collection of all of those with the 0, that is, it's like a simplicial complex. It's just you're given, but you're given the actual values of the rays, the actual lines, and then which ones correspond to cones. So this is sigma. In this case, it's in dimension 2. They're always simplicial. Simplicial means that each cone is given by exactly the number of dimension of rays in there. And so this is the case. In higher dimension, this will be sigma 0, and then we have to triangulate it somehow. So we'll maybe talk about that in a second. Okay. So, but in dimension, we're just doing dimension 2 right now. So then this thing here gives you a toric variety. So a fan, sigma, so sigma contains, I lost where I was doing all this. That's over here. So sigma contains the information of the sigma is completely encoded by the rays. I guess I'm calling them row 1 to row 4, which are elements in z to the 2 in our case here in this example, and also by this subsets of 1 to 4, which are cones. And for us, we're always going to be wanting simplicial cones. So once we take the maximal ones, we know exactly what they all are. Okay. Now then the toric land takes this sigma, and this is in the normal toric varieties package. You give it both of these pieces of information, and it gives you P sigma, which I think of as another good place for varieties to live. So so instead of projective space or product of projective spaces, we get most of the benefit of all that, those nice spaces in here as well. This is not necessarily smooth. It is in this case, but if I'd switched my deltas here, if I'd flipped these around, then it would not be a smooth variety. But it doesn't really matter. Turns out, and something that Batyrev proves is that the singularities aren't so bad. And essentially they're point-like. And so that when we intersect with this x later on, this 0 set, we're going to be able to avoid any points we want. So it'll be random enough that it will be smooth, which is actually something that is not easy in higher dimensions. So that's actually fails in dimension greater than 3. Okay, So where am I here? So we have that. So we have this P sigma, and now, oh yeah, what is the we need the homogeneous coordinate ring or the Cox ring. As they say, as David said, even don't Google for that. And but anyway, for the homogeneous coordinate ring, what it is it's going to be a polynomial ring where you have one variable for every row that you have in here. Okay. It can be over any field, but in the applications here, it's over the complexes, but in fact, I'm just going to put K. And then we're going to have variables in x1 to xn. And in our case, it's going to be x1 to x4 because we have 4 of these things. Okay. And now what are the degrees? Well, it turns out that one way to do that, here, before I go on to this, is this really? What am I really missing doing here? Basically what I want is if I take Z2 to Z4, this is going to be the placement of all my rays. Okay, so that's all these things I'm going to shove them into a matrix, except it's a tall matrix like this. And I'm going to put them in order 1, 0, 0, 1, minus 1, 0, 0, minus 1 are the rays in this example. Okay. And now I take the other side, I'm going to call that matrix A and this matrix B, and I get Z2 here. And what if you think about what this is, I get 1, 0, 1, 0 and 0, 1, 0, 1. And I want the degree of xi to equal the ith column of B. So x1 and x3 have degree 1, 0, and the other two have degree 0, 1. It's just the usual homogeneous coordinate ring of P1 cross P1. In fact, that's exactly what this is. So that's the homogeneous coordinate ring. And we can do that pretty easily in higher dimensions as well. So the homogeneous coordinate ring is just, we do exactly that. Place the rays, take the kernel, that's going to be our, actually in physics, they have, instead of calling it a degree matrix, they call it the GLSM charge matrix, okay? GLSM is generalized sigma linear model or something like that, okay? In any case, we have that. And now the sum of monomials, I wanted to maybe say something about that, but I'm going to say it in words here. How do I get the polynomials? Well, it turns out over here, I'm thinking of, I have each variable here now is sort of is coming about from, like x1 corresponds to this thing here. What if I set x1 to be 0? What do I get?
The divisor. I
get a divisor on the thing. And in fact, that divisor is going to be 1, depending on how we look at it, it's going to be either a point cross P1, like 0 or infinity cross P1, or P1 cross the 0 or infinity. In fact, those are what all 4 of these things are. And so over here, we have the equations. And over here, we have what the variety looks like. We have these 4 P1s that these 2 P1s don't intersect. These 2 P1s don't intersect. These 2 intersect at a point. This is a pictorial picture of the toric variety. That's way I think about it. And then, but here's another cool thing is I have all this. I can make a monomial in the x's given by all of this. So if I take a monomial over here, the way it works is, I'm not going to write down the equation for it, but you can make a monomial for each one of these things. And the middle one is x1, x2, x3, x4. And what it is x1, x2, and x3, and x4 are the vertices over here. So they're the walls over here, the codimensional 1 things. And this is the exponent for x4, for instance, is how far away it is from wall 4 in lattice distance somehow. So for instance, this is wall 1, and so it is on x1 equaling, on the wall x1. So this is really going to be x2. This is x2. It's that's 1 away from this wall, but this one is 2 away from this wall. So it's x3 squared and then x4. Okay, so we get a monomial. We can write down a monomial for all 9 of these things, and then the way we get the f here is we just take all those monomials, how many ever there are, figure out what their monomials are, and then take some random sum of those, and that's F. Okay. So that's that. So this is coming from the monomials are from delta. The only thing that is really a problem here is that we want this thing to be a simplicial, So in higher dimensions, we have the following situation. Suppose that our polytope is a cube, for instance. This is delta circ now. Delta over here is going to be some sort of octahedron thing. But anyway, suppose it's here. And here's my origin in the middle. I have all these, I have 27 lattice points all together. But now my one cone that I'm getting is this four-sided cone. So I have to triangulate it. One way to do it is just to make, to triangulate it somehow. So this triangulation here is triangulating is not just triangulating the fan, it's triangulating delta circ as a polytope using essentially all of the lattice points in delta circ. Okay. Actually, it turns out you don't need to use ones which are interior to facets. I mean, you can do it, but then they won't ever help matter at all. Okay, so the story then is you start with delta circ. In dimension 4, there are 500 million of those you can choose, or roughly. Then you actually take you take delta, you have to calculate from delta, you calculate delta circ maybe. If you just started with whichever one you start with, you calculate the other. And then you, from this, you triangulate it. Okay, using all of these things. And you got to make sure it has a few properties. It has to give you, you do this and you want it to be star, meaning that every simplex in the triangulation includes the origin. Because we want it to be partly descend to the fan. So we want that. We want it to be fine, which means it uses all these lattice points. And we want it to be regular. The regular part of a polytope here is that if you make it regular, then the resulting thing is projective. And if it's not, then it's not. Okay, so we want projective varieties, so we have all that. So this goes under the name fine regular star triangulation. And so basic plan is we start with that, we do it, we find a FRST of this, or find them all. That immediately gives us a toric variety and a coordinate ring. And we can also directly use the monomials in here and give us a hypersurface. That's the construction in a nutshell. What's really cool about it is that the playoff between these delta and delta circ and the combinatorics of it tell you a lot about the geometry of X. And I'll probably be saying something more about that this afternoon. Anyway, that's all for a moment. Sorry, I went over.